Hello my friends and welcome to my channel. Walter here, and today I'm going to be taking you through the October-November 2023 Further Pure Miss 1 paper. That's 9231/12. Now I hope you're going to learn a lot from what we're going to be discussing in this video. So let's get started. Alright, so we are starting with question number 1. It says, use standard results from the list of formulae MF19 to find the sum to n of terms of the form 3r squared plus 3r plus 1 in terms of n, simplifying your answer. So let's start with that very question. Here we have the sum from r is equal to 1 up to n of 3r squared plus 3r plus 1. This is the same as 3 times the sum from r is equal to 1 up to n of terms of the form r squared plus 3 times the sum from r is equal to 1 up to n of terms of the form r plus the sum from r is equal to 1 up to n of 1. So this is what we have, and if you go to MF19, the sum of squares of r will actually give you a 6th n of n plus 1 of 2n plus 1, and it's plus 3 for the sum to n, that's half n of n plus 1, like this, and then the sum of n ones will just give us n. Alright, so multiplying 3 into the bracket, we will get half n of, and multiplying these two brackets, we will get 2n squared plus 3n plus 1, and it's plus here, that's 3 over 2 of n plus 1 plus n. So this here, half n times 2n squared gives us n cubed. Then half n times this gives us 3 over 2n squared, and times this gives us half n. Alright, and it's plus this multiplied by this, we get 3 over 2n squared, and by 1 we get 3 over 2 of n, and it's plus n. Alright, so we can continue simplifying this. We have n cubed, then 3 over 2n squared plus 3 over 2n squared will give us 3n squared. And next, when we say half n plus 3 over 2n plus n, this gives us 3. Alright, so that is the sum expressed in terms of n. Let's move on to part B. Now in part B, they say, show that 1 over r cubed minus 1 over r plus 1 cubed is equal to this. And hence, use the method of differences to find this summation. Alright, so let's start by proving, okay, if we take the left hand side, we will be having 1 over r cubed, and that's minus 1 over r plus 1 cubed, and the common denominator for this two will be r cubed of r plus 1 cubed. We are going to multiply these two and minus these two. Alright, so this will be r plus 1 cubed minus r cubed. Expanding r plus 1 cubed gives us r cubed plus 3r squared plus 3r plus 1, and it's minus the r cubed that is already there. So this is r cubed, the denominator of r plus 1 cubed. Alright, so this is going to give us on top r cubed minus r cubed, that's 0. So we're left with 3r squared plus 3r plus 1, and this is over r cubed of r plus 1 cubed. So this is what we now have, and you can see that it's equal to the right hand side. That's shown. So that's what we do for the first part. Now the question continues to say, we should hence use the method of differences to find the sum to n of this form. Alright, so basically the sum from r is equal to 1 up to n of terms of the form 3r squared plus 3r plus 1 of r cubed of r plus 1 cubed should be the same as the sum from r is equal to 1 up to n of 1 over r cubed minus 1 over r plus 1 cubed. Alright, so we're using the method of differences now. So we're saying that when r is 1, we'll be having 1 over 1 cubed, which is 1, minus 1 over 1 plus 1 cubed, which is 2 cubed. And that's going to be plus when r is 2, that will be 1 over 2 cubed, and it's minus 1 over 3 cubed. It's plus when r is 3, that will be 1 over 3 cubed minus 1 over 4 cubed. So it will continue going all the way until we reach the term that precedes the last. That's when r is equal to n minus 1, which will give us 1 over n minus 1 cubed, and it's minus 1 over n cubed. Then for the very last term in this series, that's when r is equal to n, we will get 1 over n cubed minus 1 over n plus 1 cubed. So these are all the terms in the series. Now, if we add these two terms up, we get 0. These two add up to give us 0. So in the same way, this term will be eliminated, and all the terms in between, including this term here. You can also see that minus 1 over n cubed adds up to 1 over n cubed to give us 0. And what remains from this whole thing is 1 minus 1 over n plus 1 cubed. So that's what we'll be having right here. And this is the sum to n. Let's move on to part C. Part C says, deduce the sum to infinity of this. So we are saying that this sum to infinity is the same as the limit as n approaches infinity of, since we've gotten the sum to n to be this, so we are looking for its sum to infinity. So that's basically 1 minus 1 over n plus 1 cubed. So 1 minus 1 over n plus 1 cubed. So we are looking for the limit to infinity of this. So for the constant, we just get 1. But for this fraction, as n tends towards infinity, this whole thing would tend towards 0. So we have 1 minus 0, which is just 1. So 1 is the answer. That's the sum to infinity in this particular case. Number 2, prove by mathematical induction that for all positive integers n, d to the n by dx to the n of x squared e to the x is equal to x squared plus 2nx plus n of n minus 1, O of e to the x. Alright, so let's prove by induction. So I'll start by proving for n is equal to 1. The left hand side will give us d by dx of x squared of e to the x, because n is 1, which is e to the x d by dx of x squared plus x squared d by dx of e to the x, which will give us 2x e to the x plus x squared e to the x, which is 2x plus x squared of e to the x. The right hand side, when n is 1, will give us x squared plus 2x, and here 1 of 1 minus 1 is actually 0, so this part gives us 0. Alright, so we have of e to the x, and I think you can see that is the same thing we got. So we will say that it's equal to the left hand side. Therefore, true for n is equal to 1. So we're going to next assume true for n is equal to k. And if that is so, we would therefore be having d to the k by dx to the k of x squared of e to the x being equal to x squared plus 2kx. Okay, let me correct that. So it's plus 2kx plus k of k minus 1 of e to the x. Actually, everything is of e to the x. So this is what we have for d to the k when n is equal to k. All right. Now we are going to prove for n is equal to k plus 1. This means that we will be having d to the k plus 1 by dx to the k plus 1 of x squared of e to the x, which is the same as the derivative with respect to x of d to the k by dx to the k of x squared e to the x. So this is what we have. Now, we know that d to the k by dx to the k of x squared e to the x, we got that in our assumption as x squared plus 2kx plus k of k minus 1 of e to the x. All right, so we are going to differentiate this thing here, and we're going to treat this as a product. So I'm going to say, okay, to use some space, differentiating this product, we will get e to the x times the derivative with respect to x of x squared plus 2kx plus k of k minus 1. And it's going to be plus x squared plus 2kx plus k of k minus 1 times the derivative with respect to x of e to the x. So we get e to the x of, differentiating this thing, we get 2x plus 2k only from it. All right, so this is, and this plus, here we will get still the e to the x when we differentiate. So it's e to the x of x squared plus 2kx plus k of k minus 1. All right, so I'm just going to expand the brackets there. So k squared minus k basically. All right, so if we factor out e to the x, we will be having 2x plus 2k, and it's going to be plus this, which is x squared plus 2kx plus k squared minus k. So we will be having now e to the x, and here I'm going to take the x squared. So we have x squared here, and next I'm going to take the 2kx. So we have plus 2kx, and I'm also going to have the 2x here. So it's plus 2x. Next, I'll have the k squared. So it's plus k squared. And lastly, 2k minus k is k. So I'll say plus k. All right. So we have e to the x of x squared. And for these two terms in x, I'm going to factor out x. So we get 2 of k plus 1 of x when we factorize it. And for this 2, it will be k of k plus 1 that we will be having. Okay, so this is what we have. I can rewrite it as x squared plus 2 of k plus 1 of x plus k of k plus 1 of e to the x. And what we have right here is actually the same as what we have here. Okay, if we put n back to where k plus 1 is all around, it will have the same value, right? So we can actually therefore say it's true for n is equal to k plus 1. All right, so for our concluding statement, I will say, since we got it to be true for n is equal to 1, and if true for n is equal to k, it's coming out to be true for n is equal to k plus 1. Therefore, by the principle of mathematical induction, it has to be true for all positive integers n. So that's how we prove it right here. Let's go on to the next question. Now we're on number 3. It says the matrix M is given by M is equal to K0, 0, 1 of 1, 0, 1, 1, where K is a constant and K is not equal to 0 and K is also not equal to 1. So on part A, the matrix M represents a sequence of 2 geometrical transformations. State the type of each transformation and make clear the order in which they are applied. So here we've got 2 transformations represented by these 2 matrices. So the first transformation is the one that is post-multiplying. That's the first transformation. And the second one is the one that is pre-multiplying. All right. So the first transformation, which is represented by 1, 0, 1, 1, is actually a matrix for a shear, which is parallel to the y-axis. Okay, so this is what this matrix represents. And for the second transformation, this one represents a stretch which is parallel to the x-axis, all right, with a factor k, stretch factor k. So these are the 2 transformations going on right here. Let's go on to part B. On part B, the question says the unit square in the xy plane is transformed by M onto parallelogram or PQR. Okay, so on part B, find in terms of K the area of parallelogram or PQR and the matrix which transforms or PQR onto the unit square. Alright, so from what they're saying, we have a unit square and the unit square is being transformed onto a parallelogram, okay, and this is through the matrix M. Okay, all right, so what we know is if we multiply the determinant of M by the area of the unit square, which we know is 1, we should get the area of the parallelogram. And so now for the determinant of M, the matrix M is represented by K001, so K001, and it's pre-multiplying 1011, so 1011 here. So multiplying this 2, we should get K011, all right, and therefore the determinant should be K minus 0, which is just K. All right, that's the determinant. So therefore here we are saying the area of the parallelogram. So let me just rewrite this. We are saying that the area of the parallelogram is equal to the determinant of M times the area of the unit square. So that's K times the unit square always has an area of 1, like we said, so K. So basically K is the answer. That's the area of the parallelogram. So they also want us to find the matrix which transforms OPQR onto the unit square. So we want the matrix which does the reverse. So if matrix M does the forward, the inverse of M should do the reverse. So the matrix they want us to find is M inverse. Okay, and to get M inverse, we'll say 1 over the determinant, and here we will switch the positions. All right, so 1 here, K here, and for 0 and 1 we'll multiply by -1, so 0 and -1. So this is the matrix which does the reverse. So that's how we do it. Let's go on to part C. On part C, they say, show that the line through the origin with gradient 1 over k minus 1 is invariant under the transformation in the xy plane represented by M. All right. So in this case, we are talking about a line through the origin with gradient 1 over k minus 1, which should be the line y is equal to 1 over k minus 1 of x. So they want us to show that all the points on this line are invariant under the transformation. All right. So the transformation M, the matrix M, we got it to be K0, 1, 1. And if we multiply points on the original line, we should get an image like this. So this is kx plus 0y is equal to big X, then x plus y is equal to big Y. All right. So since the lines pass through the origin, we know that there we have the equation y is equal to mx. All right. So wherever there's y, we're going to put mx. This is equation 1 and this is equation 2. So equation 1 is fine. It's kx is equal to big X. Equation 2, in equation 2, where there's y, we're going to put mx. So it's x plus mx is equal to big Y. Next, we're going to say the image line is y is equal to mx. Since we are talking about an invariant line, so therefore y should be equal to mx, gives us y, which is x plus mx. All right, and it's equal to m of big X, which is kx. All right, so we're going to divide everything by x. So 1 plus m is equal to km. All right, so this is as good as km minus m is equal to 1, which is m of k minus 1 is equal to 1. Therefore, m is 1 over k minus 1. So we have proved that the gradient of these lines is 1 over k minus 1. And that's actually what they are saying here, that the lines should have gradient 1 over k minus 1. So I'll say here shown. Let's move on to the next question, which is number 4. It says the cubic equation 27x cubed plus 18x squared plus 6x minus 1 equal to 0 has roots alpha, beta, and gamma. On part A, show that a cubic equation with roots 3 alpha plus 1, 3 beta plus 1, and 3 gamma plus 1 is y cubed minus y squared plus y minus 2 equal to 0. Alright, so say here, let y be equal to 3x plus 1. Because alpha, beta, and gamma are values of x, since these are roots of this equation. Alright, and then from here, we can deduce that x is therefore y minus 1 all over 3. So in the original equation, we are substituting y minus 1 over 3 for x. So this means that we'll be having 27 of y minus 1 over 3 cubed plus 18 of y minus 1 over 3 squared, and that's plus 6 of y minus 1 over 3 and minus 1 equal to 0. Okay. Here we know that 3 cubed is 27, and 27 into 27 gives us 1. So we have y minus 1 cubed, and it's plus here 3 squared is 9. So 9 into 18 is 2. So we have 2 of y minus 1 squared, plus here 3 gets into 6 2 times. So we have 2 of y minus 1, and it's minus 1 equal to 0. All right. Let's simplify what we got. Now this gives us y cubed minus 3y squared plus 3y minus 1 plus 2 of y squared minus 2y plus 1, and it's plus 2 of y minus 1 minus 1 equal to 0. So let's simplify this again. Y cubed minus 3y squared plus 3y minus 1 plus 2y squared minus 4y, and it's plus 2 plus 2y minus 2 minus 1 equal to 0. All right. So we have y cubed here. So y cubed. So we are done with y cubed. Then minus 3y squared plus 2y squared gives us minus y squared. Then we have 3y minus 4y, which is minus y, and minus y plus 2y is y. So we have plus y here. Then lastly, we have minus 1 plus 2, which is 1, and 1 minus 2 is minus 1, and minus 1 minus 1 is minus 2, and it's equal to 0. So this is what we're getting, and that's actually what they want us to prove right here. So I'll say shown. So we are done with that part A. Let's move on to part B. It says the sum 3 alpha plus 1 to the n plus 3 beta plus 1 to the n plus 3 gamma plus 1 to the n is denoted by sum to n. Find the values of sum to 2 and sum to 3. Now I want you to remember that the 3 alpha plus 1 and 3 beta plus 1 and 3 gamma plus 1 are the roots of the equation we got right above. So they are the roots, okay, of y cubed minus y squared plus y minus 2 equal to 0, the equation we got above. So here I'm gonna say for this equation here. So I'm going to put it down here. So we are saying for this equation, the sum of roots, okay, sum of roots, we know that that's minus b over a, which is minus of minus 1 over 1, so that's 1. And the sum of product of pairs, we know that it's actually c over a, which is 1 over 1, so it's equal to 1. And the product of roots is actually minus d over a, which is actually 2. So these are the important elements of this equation, which has the roots 3 alpha plus 1, 3 beta plus 1, and 3 gamma plus 1, right? So when the question says we should find sum to 2, it basically means that we are looking for sum of squares, all right? And we know that sum of squares is the same as the sum of the roots squared minus 2 times the sum of product of pairs. So for the sum of the roots squared, that's just 1 squared, and it's minus 2 times the sum of product of pairs, which again is 1. So 1 minus 2 is minus 1. Next, they say we should find the sum to 3, right? So the equation we have is y cubed minus y squared plus y minus 2 equal to 0. We can make y cubed the subject, which will be y squared minus y plus 2. Alright, and from this we are going to consider that 3 alpha plus 1 is a root, and 3 beta plus 1 is a root, and 3 gamma plus 1 is a root, so that if we add these up, we get like sum to 3. And if we add this up, we get sum to 2. And adding this up, that's minus sum to 1, and it's plus 3 times 2, which is 6. Alright, so to get sum to 3, we are saying sum to 2, which is minus 1, minus sum to 1, which is the sum of roots here, that's 1, and it's plus 6, which gives us 4 for the answer. So that's the answer right there. Let's move on to part C. Part C, the question says, find the values of sum to minus 1 and sum to minus 2. Right. Let's start with sum to minus 1. Sum to minus 1 is the sum of 3 alpha plus 1 to the minus 1 plus 3 beta plus 1 to the minus 1 plus 3 gamma plus 1 to the minus 1, which is 1 over 3 alpha plus 1 plus 1 over 3 beta plus 1 plus 1 over 3 gamma plus 1. So when you have something like this, you should know that it's actually the same as the sum of product of pairs over the product of roots. Okay, so the sum of product of pairs, according to what we got, is 1 right here. So it's as good as we have 1 over the product of roots. Product of roots is 2 from what we got here. So it's over 2. So that's what we have for this. Next up, they want the sum to minus 2. Now, for the sum to minus 2, we are going to try to see if we can make use of a recurrence relation. So I'm going to say, since we have y cubed minus y squared plus y minus 2 being equal to 0, I am going to make 2 the subject. So 2 is equal to y cubed minus y squared plus y. And I'm going to multiply both sides of this equation by y to the n. Alright, so we'll be having this side by y to the n and this whole side by y to the n. So if we do that, on the left side we'll be having 2y to the n being equal to y to the n plus 3 minus y to the n plus 2 plus y to the n plus 1. Alright, now since 3 alpha plus 1, 3 beta plus 1, and 3 gamma plus 1 are roots to this thing, we will be coming out with this. And if we add these up, we'll be having 2 times sum to n being equal to sum to n plus 3, alright, minus sum to n plus 2 plus sum to n plus 1. So this is a good recurrence relation which we can make use of, such that when we therefore want to find 2 times sum to minus 2, that is when n is minus 2, we will be having minus 2 plus 3, which is sum to 1, and minus 2 plus 2, which is sum to 0, and here minus 2 plus 1 is minus 1, so it's plus sum to minus 1. Now sum to 1 is the sum of roots for this here, which is actually 1. So we have 1 here, and this minus sum to 0 means the roots to the power 0. So we're putting 0 here, and we get 1 plus 1 plus 1, which is 3. So here is 3, and it's plus sum to minus 1. This is what we got to be a half here. So it's a half plus a half. So 1 minus 3 plus a half is minus 3 over 2. And if we divide that by 2, would therefore get sum to minus 2 being equal to minus 3/4. So that is what we do for this particular question. Let's move on to number 5. On number 5, it says the plane pi1 has equation r is equal to I minus j minus 2k plus lambda of I minus 2j minus 3k plus mu of 3i minus k. So on part A, they say find an equation for pi1 in the form ax plus by plus cz equal to d. Alright, so here we've got the equation of the plane in this form. Okay, so technically that's the form r is equal to a plus lambda b plus mu c. Alright, so this is the form the equation of the plane is in. Now, in order for us to find the equation of the plane in Cartesian form, as they want here, we have to find the normal to the plane. So we're going to take the direction vectors b and c, and these are going to help us to find the normal to the plane. All right, so here is an illustration of a plane, and we have the two vectors. All right, one of them is b and one of them is c, and we know that this one is b and this one is c. Okay, and we are saying that we want the normal to the plane. All right, that's n, and it's a perpendicular to the plane, which we find by a vector product. So I'm going to take the two vectors and do vector product with them. So we have I minus 2j minus 3k, and we are multiplying that by 3i minus k. All right, so this is like 1 minus 2 minus 3, and we are having vector product with 3, 0, minus 1. All right, so this is what we have right here. So I am going to start by closing out these two, and we do minus 2 times minus 1 minus 3 times 0. So here we will be having 2 minus 0, which is just 2. So we have here 2i. Then I'm going to close these two. So I'm going to do 1 times minus 1 minus 3 times 3. So that's like minus 1 plus 9, which is 8. So we have 8j here. Actually, it's minus 8j because for this middle one, we put a minus. All right. Next up, we are going to be closing out this 2, and we multiply 1 times 0 minus 2 times 3, and this is going to give us 6, so that's 6k. So we have 6k here, so it's plus 6k. So this is what we are having as being the normal to the plane. This is actually n, the normal to the plane. All right. Now that we have the normal to the plane, we need also to find d, which actually we find by a dot n. All right, so a is a point on the plane, so we can have a point a on the plane, and the point on the plane for us here is I minus j minus 2k. So we are doing scalar product. I'm going to write that in column vector form, which exposes the scalars. So it's actually 1 minus 2 dot the normal, which is 2 minus 8, 6. All right, so that's 1 times 2 plus minus 1 times minus 8, which is 8, and minus 2 times 6 is minus 12. So that's like 2 plus 8, that's 10. 10 minus 12 is minus 2. Okay, so this is what we are having as d. So therefore, we will be having the equation of the plane as r dot 2 minus 8, 6 is equal to minus 2, which in Cartesian form is 2x minus 8y plus 6z equals to minus 2. And this can be reduced by dividing each term by 2. So we can write it in its simplest form as x minus 4y plus 3z equals to minus 1. So this is the answer they want us to find here on part A. Let's move on. On part B, they say the line L, which does not lie in pi 1, has equation R is equal to minus 3i plus k plus t of I plus j plus k. So on B, show that L is parallel to pi 1. Right. So we have a plane and a line. Right. So the line is L and the plane is pi. So here they want us to show that the line L is parallel to the plane pi 1. So to show that a line is parallel to a plane, it is a fact that the normal to the plane, okay, which is n, which is perpendicular to the plane, should also be perpendicular to the line L. That is, in the event that L and pi 1 are parallel to each other. So we know that for perpendicular vectors, their dot product is 0. So we're saying the normal n dot the direction vector of L should give us 0. Now the normal to the plane, we had gotten that as 2 minus 8, 6, or in simplified form, 1 minus 4, 3. So let's use 1 minus 4, 3 dot the direction vector of L is what we have here. All right, that's 1, 1, 1 in column vector form. So we want to prove if it is equal to 0 or not. So that's 1 times 1 plus minus 4 times 1 plus 3 times 1, all right, which is 1 minus 4 plus 3. 1 minus 4 is minus 3, and minus 3 plus 3 is 0. All right, so that's how we show it. That's how we show that the line is parallel to the plane. Let's move on. Now we're on part C. On C, they say, find the distance between L and pi 1. Okay, so we have the plane here and the line L. In order for us to find the distance between the two, we need to know a point that is on the plane. Let's call it point A. So for this point, let's say its coordinates are x1, y1, and z1. And we also need to know the equation of the plane. All right. So this is the plane pi 1. This is the line L. And the equation of the plane should be in the form ax plus by plus cz equal to d. All right. So with these two things, we can use the formula d is equal to under modulus ax1 plus by1 plus cz1 minus d over the square root of a squared plus b squared plus c squared. So this is actually the formula we're going to be making use of. All right. So do we have these things? If we go back, the equation of the plane, we got it to be x minus 4y plus 3z equals to minus 1. So that's what we're going to use right here. So the plane pi 1 has equation x minus 4y plus 3z equals to minus 1. And the point, a point on L1, okay, which I'm going to call A, will have coordinates. We'll take this part of the line L, which is a point on the line L, which is minus 3, 0, 1. So minus 3, 0, 1. All right. So we're going to make use of this, where I'll say this is equal to 1 of minus 3, minus 4 of 0, plus 3 of 1, and minus d will be plus 1. Minus d is like we're taking minus 1 to this other side. And it's all over the square root of 1 squared plus minus 4 squared plus 3 squared. All right. So let's simplify this. This is as good as, on top, we'll be having minus 3 minus 0 plus 3. So all that gives us 0. So we are left with a 1 on top. And at the bottom, if we simplify this, that's 1 plus 16 plus 9. We will get root of 26. Okay, so this is actually what we have, which technically is 1 over root 26. So this here is the answer that they're looking for. Let's go on to part D. On D, they say the plane pi2 has equation 3x plus 3y plus 3z equals to 1. Find a vector equation of the line of intersection of pi1 and pi2. All right. So we want to find the line of intersection between two planes. We have the two planes pi1, which we said has equation x minus 4y plus 3z equals to minus 1. So let me write that down. So that's x minus 4y plus 3z equals to minus 1. And we have been given the plane pi2, which is 3x plus 3y plus 2z equals to 1. All right. So I'm going to set z to be equal to 0. And when we do, we will be having x minus 4y equals to minus 1 and 3x plus 3y equals to 1. All right. And I'm going to solve these two equations simultaneously. So I'm going to call this equation 1 and this other equation 2. All right. So from equation 1, I'm going to make x the subject. So x is equal to 4y minus 1. And I'm going to substitute that into 2, where we'll be having then 3 of 4y minus 1 plus 3y equals to 1, which is 12y minus 3 plus 3y equals to 1, which is 15y equals to 4. And we get y to be 4 over 15. That also means that x will be 4 of 4 over 15 minus 1, all right, which is 16 over 15 minus 1, which is 1 over 15. So this is the value of x, all right. So we have now gotten this. So what that means is we have found a common point for the two planes. So therefore, the common point, all right, which is actually a point on the line, okay, of the line of intersection of the two planes, that's 1 over 15, 4 over 15, and since we had set z to be 0 and 0, so this is what we got. Next, we are going to look for the common perpendicular of the normals, all right, the common perpendicular of the normals, and we are going to find that by taking the normals and doing vector product with the two normals. So for the first plane, the normal is 1 minus 4, 3. All right. So I'm going to take 1 minus 4, 3 and vector product with the 1, 4, pi 2, which is 3, 3, 2. So cross 3, 3, 2. All right. So if we do vector product with these, I'll close here, and minus 8 minus 9 is minus 17. So we have minus 17 here. Then I close out here. So 2 minus 9 is minus 7. But I'll put a minus on it, so it becomes a 7. Then lastly, close out here. Then this 3 minus minus 12 will give us 15. So we have 15 down here. So this here is the common perpendicular of the normals, which also happens to be the direction vector of the line of intersection of the planes. So therefore, the equation of the line of intersection will be r is equal to a point on the line, which we got to be the common point, which is 1 over 15, 4 over 15, and 0, okay, plus s of the direction vector, which is the common perpendicular of the normals, minus 17, 7, and 15. So this here, what we have, is the line of intersection of the two planes. Let's move on to the next question, number 6. It says, the curve C has polar equation r is equal to e to the minus theta minus e to the minus half pi, where theta ranges between 0 and a half pi. So on part A, sketch C and state in exact form the greatest distance of a point on C from the pole. Alright, so in this particular case, we are going to consider a polar plane, and since we have been given a range from 0 to a half pi, I am going to divide it into 4 intervals. So we'll go in pi over 8 increments. So we'll be having 0, pi over 8, 2 pi over 8, which is pi over 4, 3 pi over 8, and 4 pi over 8, which is half pi, like this. Next, we are going to have the table of values with these theta values, and when we substitute into the equation theta as 0, we get r to be 0.79. When theta is an eighth pi, r is 0.47. When theta is a quarter pi, r is 0.25. When theta is 3/8 pi, r is 0.1. And lastly, when theta is a half pi, r will be 0. So we are going to plot these points on the polar plane. And when we do, we join the points up and we get something like this. So I'm going to make the sketch here. So we have the pole here, and this is the line theta equal to 0. And I think you saw that the graph was something like this. So this is what we have right here. Now, the greatest distance from the pole, I think you can see that it corresponds to this point, all right, where theta is 0. So we're saying the greatest distance from the pole occurs when theta equals to 0, and when theta is 0, we'll be having r is equal to e to the 0 minus e to the minus half pi, which would give us 1 minus e to the minus half pi. So since they want the answer in exact form, this is the answer we get for the greatest distance from the pole. And that's how we do it for part A. Let's move on to the next part. On part B, they say, find the exact value of the area of the region bounded by C and the initial line. All right. So we are saying here, to find the wanted region, which is this whole region here, all right, we are going to integrate. We're going to use the formula A is equal to the integral from alpha to beta of half r squared d theta, which in our case will be half of the integral of r squared with the limits 0 to a half pi of r squared. Remember, r is e to the minus theta minus e to the minus half pi. So we're going to have that here. So e to the minus theta minus e to the minus of a half pi squared, and it's with respect to theta, right? So let's expand what we have. So it's like we have half of the integral 0 to a half pi, and expanding this we get e to the minus 2 theta minus 2e to the minus half pi of e to the minus theta plus e to the minus pi, and it's with respect to theta. So now integrating, for integrating e to the minus 2 theta, we get minus a half of e to the minus 2 theta. And here, if we integrate e to the minus theta, we get minus e to the minus theta. So that minus with this minus will give us plus. So we have plus 2e to the minus of a half pi, which is a constant, of e to the minus theta. Then integrating this, we get plus e to the minus pi of theta, and the limits are 0 to a half pi. So we have half, and now substituting a half pi into this, here we will have minus a half of e to the minus pi. Then substituting it here, we'll be having 2e to the minus of a half pi of e to the minus of a half pi. We'll simplify this later. And here we'll be having half pi of e to the minus pi. And substituting 0 all the way, here we will get minus a half. And here, substituting 0, we will just get 2e to the minus of a half pi. And lastly, on this part, substituting 0, we get 0. Right. So I'm going to close this. Let's simplify what we got. Right. So we have a half, and we have minus half e to the minus pi. Then if we multiply this 2, we add up the powers and we get e to the minus pi. So that's plus 2e to the minus pi. This part is the same, so it's plus half pi e to the minus pi. And here that's going to be plus a half and minus 2e to the minus of half pi. So this is what we have right here. All right. Now we still have the half, and minus half e to the minus pi plus 2e to the minus pi will give us 3 over 2 of e to the minus pi. And we still have the half pi e to the minus pi, and we have the minus 2e to the minus half pi, and we have the half. All right. And I'm going to multiply into the bracket to get 3 over 4 e to the minus pi plus a quarter pi of e to the minus pi minus e to the minus half pi plus a quarter, which is the exact answer. All right. Here that said we should find the exact value. So this is the exact value of the area that we've gotten here. Now let's move on to part C. So on part C, it says, show that at the point on C furthest from the initial line, 1 minus e to the theta minus half pi minus tan theta equals to 0. And verify that this equation has a root between 0.56 and 0.57. All right. Now here we're talking about a point on C furthest from the initial line, and you need to know that for the point furthest from the initial line, dy by d theta is equal to 0. All right, so this is something that you need to know. So basically, if we go back and take the equation of the curve, which is r is equal to e to the minus theta minus e to the minus half pi. So let me write that down. So I'll say here, since r is equal to e to the minus theta minus e to the minus of a half pi, and we also know that y is equal to r sine theta, which leads us to having r to be y over sine theta. So we can therefore say in place of r, we can put y over sine theta is equal to e to the minus theta minus e to the minus of a half pi. So we have done this so that we can have an equation which is of y in terms of theta. So here we'll be having y is equal to e to the minus theta minus e to the minus of a half pi of sine theta, like this. All right. So we can now find dy by the theta. So dy by the theta is equal to, and we're now doing a differentiation of products. So it is going to be sine theta times the derivative with respect to theta of e to the minus theta minus e to the minus of a half pi, and that's plus e to the minus theta minus e to the minus of a half pi times the derivative with respect to theta of sine theta. So here we will be having sine theta, and differentiating this, we will get minus e to the minus theta. All right, and this plus, here we still have the e to the minus theta minus e to the minus of a half pi, and differentiating sine theta, we get cos theta. All right, so this is what we have right here. Now we are saying that since we are talking about a point furthest from the initial line, dy by the theta should be equal to 0. All right, so we are saying that this is 0 and this whole thing is equal to 0. So what I'm going to do here is I'm going to divide both terms by cos theta. All right, so if we divide here by cos theta and here by cos theta, and on the right side again by cos theta, we will be having on the left side minus e to the minus theta of tan theta, and here they will cancel and we'll be having e to the minus theta minus e to the minus half pi equal to 0. All right, now they are saying that they want us to prove that we get this thing here. So let's see if we can get that. So we are going to divide all the terms by e to the minus theta. So let's do that. And when we do, here we will remain with minus tan theta, and here we will get 1, and here we will get e to the theta minus a half pi if we subtract the powers, since we are dividing and the base is the same. All right, so that's what we'll be having, and it's all equal to 0. So it's now more like what they want us to have it to be. Okay, so I can rearrange it so that it's now 1 minus e to the theta minus of a half pi, and it's minus tan theta equal to 0, and that's what they want. So I'll say here shown. Now the other part of the question says, and verify that this equation has a root between 0.56 and 0.57. All right, so here I'm gonna say let f of theta be equal to 1 minus e to the theta minus half pi minus tan of theta. Okay, so we are going to look for f of 0.56 and f of 0.57 to see if we will get a sign change from this. So if we substitute 0.56 into this equation, we get 0.00912, and substituting 0.57 into this, we get minus 0.00856, and I think you can see here that we actually have a sign change, and since we have a sign change, we have a positive and a negative, we can say therefore the root does lie between 0.56 and 0.57. That's the proof. So that's how we do it right there. Let's move on. Now we are on question number 7. It says the curve C has equation y is equal to f of x, where f of x is equal to x squared over x plus 1. Find the equations of the asymptotes of C. Alright, so here we start with the vertical asymptote, which we find by setting the denominator to 0. So we get x to be minus 1 as the vertical asymptote. Next, we can see that we should be having an oblique asymptote because the degree of the numerator is greater than the degree of the denominator by 1. So we get that by dividing x plus 1 into x squared. X into x squared is x, and x times x plus 1 is x squared plus x. We subtract. X squared minus x squared is 0, and 0 minus x gives us minus x. Alright. Then x into minus x is minus 1, and minus 1 times x plus 1 is minus x minus 1. Alright. So minus x here, minus 1, and we subtract. And minus x minus minus x is 0, and 0 minus minus 1 gives us a remainder of 1. But what we're concerned with is the quotient, which we got here. So therefore, the oblique asymptote is y is equal to x minus 1. So these are the asymptotes. X equals to minus 1 and y is equal to x minus 1. Let's move on to the next part. They say here, find the coordinates of any stationary points on C. Right, so we're going to take the equation of the curve y is equal to x squared over x plus 1. Then we're going to find dy by dx for the stationary points, because we know that at the stationary point dy by dx is equal to 0. So dy by dx using the quotient rule should give us x plus 1 times the derivative with respect to x of x squared minus x squared times the derivative with respect to x of x plus 1 all over x plus 1 squared should give us 0. So we'll be having 2x of x plus 1 minus x squared equal to 0 after multiplying both sides by x plus 1 squared. So we have 2x squared plus 2x minus x squared equal to 0, which is x squared plus 2x equal to 0. So x of x plus 2 is equal to 0. So the values of x we have are 0 or x is equal to minus 2. Alright. So since we want them as coordinates, I'll have a little table of values. So I'll say here, these are values of x, which are 0 and minus 2. And when x is 0, substituting 0 into the equation, we get y to be 0. So we have 0 here. And if we substitute minus 2, so this is the value of y, substitute minus 2 into the equation, we get y coming out as minus 4. So minus 4 here. So the coordinates of the stationary points will be 0, 0, and minus 2, minus 4. Next up is part C, where they say we should sketch C. So we can make the sketch of the graph right here. So we have the axis. Here we have the vertical axis y and the horizontal axis x and the origin. Now we have the asymptotes. Vertical asymptote is x is equal to minus 1. Alright, so I'll draw that line here. So x is equal to minus 1 here to intercept at minus 1. We also have an oblique asymptote, which is y is equal to x minus 1. So it goes like this. So considering the fact that we have two stationary points, one at x equals to 0 and the other one at minus 2, minus 4, it means that we'll have our graph like this, intercepting at 0, 0 here, and the other part will be like this. So this is the graph we will have, all right? This is at minus 1. So that's the graph C that we have right here. Let's move on. On part D, the question says, find the coordinates of any stationary points on the curve with the equation y is equal to 1 over f of x. Now, y is equal to 1 over f of x is the reciprocal graph, and we are going to consider the turning points of the original graph, which are at 0, 0 and at minus 2 and minus 4. So I'll say here, for y is equal to f of x, stationary points are at 0, 0 and at minus 2 and minus 4. Now, for y is equal to 1 over f of x, the stationary points will be, okay, so we know that if we have a graph of y is equal to f of x and it having two stationary points, one of which is a minimum, the one you can see here, it means that at that very same point the reciprocal graph should have a maximum, all right? However, if we take the point 0, 0, the x coordinate doesn't change, and we do the reciprocal of the y coordinate to be 1 over 0, then 1 over 0 is infinity, and having that for a y coordinate means that the reciprocal graph will not have this point as a stationary point. So this point will not be a stationary point for the reciprocal graph. So we're going to consider the point minus 2, minus 4. The x coordinate doesn't change, and we do the reciprocal of the y coordinate, which will give us minus a quarter. So this here is the coordinate of the stationary point for the reciprocal graph. Let's move on. On part E, they say, sketch the curve with the equation y is equal to 1 over f of x and find in exact form the set of values for which 1 over f of x is greater than f of x. Alright, so let's go back to the original graph. Now we know that we can derive or get the graph of the reciprocal function from this graph of the original function. So we have a few things to consider. The first thing to consider is the fact that where our original graph intercepts the x-axis, we will have the reciprocal graph having a vertical asymptote. So it intercepts the x-axis at this particular point, which means that we should have a vertical asymptote for the reciprocal graph. Next, we are going to consider the fact that where the original graph has a vertical asymptote, we will have that x value being an intercept for the reciprocal graph. So the graph will intercept the x-axis at this particular point here. Next, we're going to consider the fact that we had gotten on part D that the reciprocal graph has a stationary point at minus 2 and minus a quarter. So that means that we should be having that turning point, stationary point around here. And you should appreciate the fact that since the original graph had a maximum, the reciprocal graph will have a minimum. So this point here will be a minimum for the reciprocal graph, since the original one was a maximum. Next, we're going to consider the fact that the original function is y is equal to x squared over x plus 1. and the reciprocal graph, so this is like for f of x, right? And for 1 over f of x, it's x plus 1 over x squared. Now, if you look at the graph, y is equal to x plus 1 over x squared, you can see that the degree of the numerator is greater than the degree of the denominator. And this therefore means that the x-axis is a horizontal asymptote. So we're going to have a horizontal asymptote right here. Okay, the x-axis is a horizontal asymptote. Lastly, we're going to consider that these graphs intercept at y is equal to 1 and y is equal to minus 1. So we should expect at y is equal to 1, these graphs to intercept. However, for y is equal to minus 1, we will not have an intersection here, since when x is equal to 0 on this y-intercept, this graph is undefined. Okay, so I think we now have an idea of how the graph is like. So coupled with the knowledge that where the original graph is increasing, in other words, where its gradient is increasing, the reciprocal graph will be decreasing, and vice versa. The graph should come out like this. Pass through here, minimum point, then rises like this. Then on the other part, it comes like this. So this is how the graph will be like. So let's make the sketch down here. So we will have the axis and the graph coming like this. So this here is the reciprocal graph. It intercepts here at minus 1. Now they also say we should find in exact form the set of values for which 1 over f of x is greater than f of x. Alright, so here we are considering the fact that these two graphs intersect at y is equal to 1. So if I draw a horizontal, it has to pass through the points of intersection like here. Okay, so this point here and this point here are the points where these two graphs intersect. I'll say the x value here is alpha and the x value here is beta, and this is the line y is equal to 1 that I have drawn. So in order for us to solve the inequality 1 over f of x, as they want, is greater than f of x, we have to find the values of alpha and beta. Right, so these values are where the graph of f of x intersects with the line y is equal to 1. So the graph x squared over x plus 1, which is f of x, has to intersect with 1. Okay, and we multiply both sides by x plus 1 so that x squared is equal to x plus 1. Then we move everything to one side so that we have x squared minus x minus 1 is equal to 0. And now, solving this equation by the quadratic formula, it will be x is equal to minus of minus 1 plus or minus the square root of minus 1 squared minus 4ac over 2a, and this will give us 1 minus root 5 all over 2, and x is equal to 1 plus root 5 over 2. So these are the two values. Okay, this is alpha and this is beta. Alright, so now that we have these two values, we can now solve the inequality. Okay, we can now solve this inequality. Alright, so you need to understand that the inequality says 1 over f of x is greater than f of x, which means, in other words, the graph in red, which is the reciprocal graph, is greater or vertically above the graph in black, which is the original function. So if you consider values that are less than minus 1, you can see that the reciprocal graph in red is vertically above the graph in black, which means values of x that are less than minus 1 are a solution. So that's the first solution right there. X is less than minus 1. Next, we look at values that are between alpha and beta, excluding x equal to 0. You can see that for these values, the graph in red is vertically above the graph in black. So we can say that for values between alpha and beta, which is values between 1 minus root 5 over 2 and 1 plus root 5 over 2, excluding x being equal to 0, these again are solutions to this inequality. So what we have here is the answer. That's the solution. And that's how we do it.